The last few sessions I spoke too long, given the amount of memory I have in my camcorder, so I lost, not recorded, about 10 minutes or more of the last recording session, so I had to delete something and I'll have to repeat something. So the last session, I just gave you the definition here that a graph is defined to be k-regular if every node in that graph has degree k. Right? So that's a definition that we'll need for this proof, and this is now what, the third I think actual concrete proof of that we've done so far, and it's an example of a proof by construction, meaning that you actually build something to to prove something. And in this case, here's the theorem ID, and the theorem statement is that that there is a graph with n nodes, and this n has to be an even number and greater than 2. So in other words, 4, 6, 8, 10, okay? And so that there is a graph with n nodes where n satisfies this, and that graph is 3 regular. Right? That's the theorem statement, that there exists, it's possible to have a graph of that kind. Okay? Now to prove that that's true, that it is possible to have such a graph, well, you actually build one. Right? You construct it. That's your proof that it exists by actually building the thing. So how to go about doing that? So proof statement. Right. So we're going to actually build the graph, construct it, and that will be our proof that it's possible that it exists. If we build it, then obviously it exists. Okay. All right. So how do you build a graph? Well, what is a graph? Well, we've done this earlier. It's defined as the two sets, so the set of vertices and the set of edges. So we have to show that there is a graph with n nodes that is 3 regular, where n satisfies this property. Okay? So let's construct a graph that does have n nodes. So here's the set of nodes, and we'll just label them from 0 to n minus 1. So that's pretty easy, right? So we have our n nodes. So that part's been done. Now the second part is the set of edges. Now that's the trickier part, a lot trickier. So often in a mathematical proof, when you're proving it, you'll have some flash, some epiphany. You say, that's like you've found an approach, a way to go about it, and often that's an act of creativity. So here's as I see it, the essential idea to showing that you can find a graph with n nodes that is 3 regular. In other words, every node has 3 edges connected to it. It's oh god, I keep forgetting the what's the name? What do you call that? The number of edges connected to it. Degree. Yeah. So every node has 3 edges connected to it. So here's an example, not the general case, not for general n, but for 8 nodes. So that's often the way. If you don't know how to tackle it generally, go for a concrete case, specific case. So I'll try it for 8. So the essence of the idea is connect up the neighbouring nodes, and then have connections, edges across. So we've got this circle or oval. So you space out more or less evenly the nodes, let's say 8 of them, because that 8 satisfies this condition. Now it's a special case, of course, but you can do it for 6, 8, 10, 12. By that stage you've probably got an idea of how to do it. And then you can generalize this idea to this. Now here is your general solution, but getting to that is not at all evident, not obvious. So start it this way visually is easier. Now what I found surprising in Sipser's text is he did not draw this diagram. I found that puzzling, because it seems to me it's such an obvious way to get to the solution, to get to a good proof. Okay, so by construction you connect the neighbouring nodes, and then you connect the cross nodes, so to speak. So I call these outer edges, right? The outer edges, and these ones that go through across the circle, call those inner edges. And by doing it this way, like by connecting 0 to 4 and 1 to 5 and 2 to 6 and 3 to 7, you can just see, just by visual inspection, that every node has a degree of 3. Right? There are 3 edges that connect to each node, so it satisfies. So this graph here is 3 regular, by definition. Okay, and you could do something similar to the case of n is 10. You can do it again, n is 12, 6, 14, and so on. So you get a pattern, and then you go for the algebra. I mean and you then go for the generalization. What would the formula be? The set of edges that would be for the general case for n, and it's this. So that would be sort of like a second step. But the essential, the creative idea would be doing this. So, with the outer edges and the inner edges. Well, that's as I see it. Okay. Now, so you got here the union of 3 sets of edges. Now this I to I plus 1, well, that would be like 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7. Then you've got this one, that's the last one to connect up again. So 7 to 0 for n is 8. I suppose you need that for the general case. And then these ones, what are they? They are the cross edges. Okay, and you put those 3 sets together, and you construct a graph that is 3 regular, right? And where n is an even number greater than 2, and it works. You've actually constructed a graph that satisfies this the theorem statement. There is such a graph. It can be done. So by constructing it, you proved that it does exist. So it's an existence proof. It's a proof that there is. You've shown that there is a graph with these properties. There it is. Well, here. This is the general case. That's a specific case. Okay, so you've done it. So that's an example of a proof by construction. You build it, you construct it, and once you've constructed it, its very existence is the proof that it can be found, that there is such a thing. So that's an example of a construction proof. Now the next 2 we will do will be proof by contradiction. You can probably guess what that's involved in. And the following one will be proof by induction. And then after that I'll do problem solving. And then we get into the next chapter, chapter 1, on languages. And the first topic, I think, is finite automata. Automata, that's plural of automaton. What's an automaton? A device, an abstract machine that computes, that calculates. But we'll talk about that kind of thing at length in the next chapter or so. So I'll stop there.